Welcome back. We're still doing practice on the class of problem they call heat lost equals heat gained, where there are two things happening, one that releases energy and another one that absorbs it and does something with it. In this case, we're burning some pentane, so we have a pentane reaction that's giving up energy or releasing energy, and on the other side, that energy is going into heating up some water. Heating up water just means changing its temperature, so we'd calculate the energy over here using mc delta T. And on the other side, the pentane burn is a chemical reaction, and we usually find those with energy equals N delta H, or cross multiplication if you're into that. Generally, there will be one side of these questions where you don't know enough to calculate anything, like here for the pentane. They told us it's delta H, but we don't know the energy released, and we don't know how much pentane was used, so we're kind of stuck here. And then there will be a side where you can calculate stuff. For the water, they told us the mass was 500 grams. We know the specific heat for water, and they told us the temperature change was 13 degrees, 13.5, sorry. So start on the side where you can actually get something done. 500 grams, 4.19 joules per gram degree Celsius, 13.5 degrees for our temperature change. And because I said grams here, this has to be joules per gram degree Celsius, so our energy is going to come out in joules. 500 times 4.19 times 13.5, I get 28,282.5 joules, or divide by 1,000 and you get 28.2825 kilojoules. And the golden rule for these questions is the energy that you find on one side has to match the energy on the other side, because all this energy in the water came from burning pentane. If the water took up 28 kilojoules, we can say, pentane, we know you released 28 kilojoules because we just saw it. 28.2825 is our E on both sides. And that equals an N that I don't know, it's the number of moles of pentane burned, times, and they generously gave us the delta H, 3,244.8 kilojoules per mole. As usual, I'm suppressing the negative sign because it's just not important for calculations like this. If we do 28.2825 divided by 3,244.8, this is going to be small. Our number of moles is 0.0087163. I hope that's enough decimal places. Moles of pentane. Sadly, they did not ask for moles of pentane. They asked for grams of pentane. So one more step. Mass equals number of moles times molar mass. Our number of moles is 0.0087163 times the molar mass. Sadly, we do not have the mass of pentane, molar mass of pentane, so one more step. Pentane, you can look it up in the data book, is C5H12. Carbon's 1201, so 5 carbons are 60.05. Hydrogen's easy, 12 hydrogens is 12.12. Our molar mass is 7217. Point 0.0087163 times 7217, and I get 0.62906 grams of pentane. And having gotten here, let's look at significant digits. We have 3 significant digits in the mass and the specific heat and the delta T, so definitely 3 coming out of that side. What else did I use? 3244.8 has 5 sig digs. That's certainly not our problem. The molar mass had 4. So yeah, our worst measurements had 3, so we should trim this down to 0.629 grams, and that ought to do it. I'll run through this part real fast using cross multiplication just to show you that the same stuff happens. It doesn't change that much. If you do this by cross multiplying, they told us the delta H here, and you would think of this as I get 3,244.8 kilojoules for every 1 mole of pentane. And the question is, what if I didn't make 3244.8 kilojoules? What if I only made 28.2825 kilojoules? How many moles of pentane are we talking about now? This energy is much smaller than the recipe amount, so this, of course, will be much smaller than 1 mole. We know that. If you cross-multiply this, you'll do 1 times 28.28 divided by 3244, and to nobody's surprise, the same number comes out. And that's moles of pentane. So, formula good, cross-multiplying also good. Just set it up with the two, gather the information for each side when you have a problem like this. Very often there's a chemical reaction side and a temperature change side, and then just start collecting all the data that you have for each side. And remember, there will be one side where you can't get anywhere. That's okay. Try the other side. There's got to be one side where we gave you enough information to get moving, otherwise the problem's hopeless, and we don't do that to you very often. See you in the next one.